find me the derivative. What's notation for derivative? You guys are in the back of your homework spirals. Sorry for those of you guys just joining us. I just started the recording. But find the derivative. Who is that? F prime of x. And the slope of the tangent line, not all the slopes, but the slope, isn't that going to be an f prime of a? Right? Like a specific one? Followed by the equation of the tangent line, isn't that going to look like a y minus y1 equals m times x minus x1? Ready, set, go. Go. See what you can do. Do what you can see. Huh? See what you can do. As they're working on that opener, for those of you guys that just joined, I'm going to freeze the screen and show you what we did at the beginning of class. I added in forever card number 6 finally, so that you guys can get caught up in your forevers with 7 and 8, and today we'll see 9. So forever card number 6 is this guy right here. There's some color coding on the actual wall. If you check out the card, this is just on my phone. But pause the video to get down to your asymptotes card, an important one that ties together lots of ideas from last chapter. But otherwise, returning to notes and then working on the opener. And then we're going to some concepts. They copied down these 2 pages of notes at the beginning of class to get them ready for today, just skipping 1 line each if you want to do that to be able to go with us in just a second. Alright, here we go. I would have used the limit definition with an h.
What?
Of f of x plus h minus f of x. I wouldn't kill a seal though. I would put my parentheses all over h. I would not kill a puppy. I would foil. Distributing my negative. I would not lose track of what I'm doing or make it illegal. I would keep writing my limit. I would cancel out the things. Oh.
Wait, is it minus x squared?
Whoa.
Never seen that one.
It turned into like the cursor instead of the pen. Alright. Thanks.
Oh, okay.
I would see a common H and be like, yay! John, did it work out okay? Sorry.
Yeah.
What you were looking at?
Yeah.
Still keeping it legal, still rewriting my limit. It's like randomly stopping. If you have an expression with a square root, not writing a limit is like just stopping to write the square root. You can't make that stop. Stop writing. I don't know, there's no nice way. Have to keep rewriting the limit or else the whole problem changes. Our h is reduced away, which was the whole point. And how do we finish this problem? Plug it in, we get 2x. What is my derivative function? F prime of x equals 2x. That was the derivative function. Boop, boop. Got him. Who is this? All the slopes of the tangent lines at the x values of an original function f. So when they say find the slope of the tangent line, which tangent line? Well, the tangent line to this graph at this point. How do I find the slope? I plug in to the derivative function, the x value 2. That will find me the slope to the graph of f at the x value 2. Plug it in, and 2 times 2 is 4.
Wow, that's some big math.
Check. So then what's my last goal?
2.
Stop, go find the tangent line. Come on, you guys can make an equation of a line. I got you a slope, there's a point. All you're going to do is go find your y1. Oh, that's like algebra stuff. Go find your y.
Why?
Because.
Why?
On the line.
It is. How do you find why?
Exactly. Kids get stuck on it all the time, and yet it's algebra. Come on, find your y. Think of what you've been given. An x and a function.
Plug in the 0.
Plug in the 0.
Make it 0.
No. those are called the zeros. We don't want the zeros, we want the y.
Yeah.
Okay, double check your group if you haven't yet already. Have you done y minus y1 equals m times x minus x1? Kyrie, come here. You go to the library to...
How about this 9?
In the library. Okay, so it was easy as right there, because all you had to do was y minus, well, weren't you doing at 2, which means you needed the derivative at 2, which means you needed the y value at 2. So all you had to do was plug in 2 and say 2 squared plus 1 is 5.
Oh,
Bruh.
I did 2 times 2 squared. I did 2 times 2 squared.
Awkward.
That's real awkward.
How do you find the y?
Also talking
You
about
could have found it way back here and said, oh, the y that goes with the x is going to be 5. Something so easy and hard.
I did 2 times 2 squared.
Now here's the cool thing in calculus. Guess what? If you could make it match like on a multiple choice, you could just stop there and be like, yeah, whatever, I'll figure it out if I need to. But just a quick heads up, if you're matching in the back of the book, the odds, right, or on CalcChat, they're going to probably get it into y equals mx plus b form. So you could go ahead and, well, sometimes you could see it like this. That's possible. They might write it in like a vertex form, x minus h, k sort of thing. Or they could actually get it all the way down. 4x minus 8 plus 5 minus 3. This is your first real introduction to making it match how there could be 3 different forms of the exact same right answer, but there will only be one in the multiple choice options. Well, not so much know all 3, but have one correct representation and be able to make it match with whatever form they put. So if you see it mx plus b, you're like, okay, I better distribute and get it all to one side. If you see it all to one side, be able to think, okay, what if y was by itself? And this is just the tip of the iceberg on that idea. Making it match. Ask BC kids how important that is. All right, in your notes, let's talk about some technical stuff. In your notes, let's talk about some technical stuff. To derive or to differentiate, these are verbs. What are verbs? Action words, right? Action.
Baby.
So if you are deriving, me crazy, if you are deriving functions or differentiating functions, yes, differentiate is an English word too, that's when it starts to get a little bit messy. Because if you're distinguishing something, some people could call that differentiating, and you're like, oh, you're deriving? No.
Absolutely not. Blasphemy.
And you don't have to stay, you can just leave it. Verbs. So that means to take the derivative. Okay? To derive or to differentiate is to take the derivative in math. Notation, there's a lot of different ways of showing this. To show the verb, careful, to show the verb, not the noun. not the noun. The noun would be way down here underneath the derivative of a function. That could be f prime of x. That could be dy dx. That could be dx of a function. I don't know, it gets awkward. There's some weird ways of showing it. But the most common ones that you guys are going to see are f prime of x or dy dx. Those ones are nouns. The verb would be ddx. Taking the derivative with respect to. If you see ddx, that's the verb. It's like take the derivative of or derive whatever follows. Technically take the first derivative of. That's usually the best way of showing the verb, of showing the action, of showing you need to do this. Down here, it's already been done, or you're trying to look for the final product. The verb, it's time to derive. The noun, it's already been done. Okay. Differentiation. Differentiation. That's a noun. However, it's not a noun for the derivative. What's usually going on when we have a shun word? You guys think of some shun words? Declaration.
Shun?
T-I-O-N words.
Oh.
Agglomeration. Collaboration.
Nice. Shunning?
What? Communication. I'm looking for nouns. These are all nouns. Wait, communication's good, right?
Yeah.
Communicate is a verb. Communication is
The act.
The act of that.
the act of that.
The act of the
So differentiation is the act of deriving. Does that make sense?
Yes.
Deriving, or, okay, we'll use the other verb, right? What's the other way of saying it? Or differentiating. Oh, differentiation is the act of differentiating. Oh. So it's not talking about the final product, like the derivative down here. It's not talking about the final product, it's talking about the act of. It's a noun kind of encapsulating the act itself, or describing, not describing, that's adjective. It's referring to the act that is being done. So differentiation is the noun referring to the act of what these verbs are doing, deriving, differentiating. Differentiation. You can also think not just the act, but sometimes people also talk about the process of. The act or the process. This is going back to English a bit, yeah. Differentiable. Not a verb, not a noun, but an adjective. An adjective. We don't say adverb. Those ones end with ly usually. Describing a verb quickly as an adverb. Differentiable. That's describing a function.
Everything's right.
It's a description of a function. Able, right? Able to be derived, which also means derivative exists. Because guess what? A derivative is a limit, yeah? Right? Definition of derivative, the limit definition of derivative. All derivatives are limits. Can limits ever not exist? Ooh, so derivatives cannot exist sometimes? Ooh. Can anybody think of, getting ready for this whole connection between differentiability, that's even a bigger word, but you guys get the idea, right? Differentiability. The ability of a function to be derived. In continuity, getting ready for this card. Derivatives are slopes of tangent lines. Don't think about rates. In real life, like motion, it's really hard for us to visualize some sort of practical example of a rate not existing. That's complicated. It's either a rate 0 or a rate's a number, but how can your rate not exist? But slopes. Can you think of any type of slope? Linear slope. That would not exist. Well, that's a special one, but actually that's equal to 0, so that exists. It's just really boring. Y equals 2.
Oh.
Nope, would still be flat. Would still be 0. But what about x equals 2? What about any vertical line? Can you see that? The slope is 0. It's really flat and really boring. It's not sloped up. It's not sloped down, right? Can you ski that? No, without a parachute, you're going to die, right? So, what if, wait a minute. What's a function that has a slope of this? Think about all your basic graphs. There is one. Actually, there's two. A function that, if you were to skim it, does go vertical. Not ln, because ln keeps on getting closer, 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 closer to vertical, but never really gets there because of that asymptote. Think of your basic graphs. Turn in your notes. You guys can find your basic graphs, right? The very, very beginning of notes. I think it was like that 3-count card. Or if you have your Trevors. Trevor number 2. Look at all those graphs. Which one goes vertical? Not x cubed, but I think you're looking at the right one. X cubed is this guy. He goes flat. He goes 0.
Oh.
No, x squared just goes flat too. I mean, he goes steeper and steeper. Huh?
The
Cube root. When would derivatives not exist? That's the question we're trying to ask. And by derivatives, we can also think slopes, but not just slopes, also limits eventually. How about this guy? Does he go vertical? Yeah, he does. Where would this guy, where would his slope not exist? At, do you see it? 0. So ready? Verb. Take the derivative of the cubed root of x, which we're not going to do with the limit definition because that one's just gross. P.S. You would have to multiply by a conjugate, but in a way that they would cancel out when you multiply, so you would need the cubed root of x squared, and that's not really conjugate, and that's gross. But anyway, let's just say if you took the derivative, at or such that x equals 0 does not exist. And technically, not just does not exist, it's actually a positive infinity. This is how you can see that a vertical line has infinite slope, which is why we always called it undefined. It's not that it's undefined, it's infinite, so we can't actually say it as a number. And we're not teaching Algebra 1 kids infinity symbols, which maybe we should. But if you see, the slope is really low, getting closer and closer and closer to 0. But as we go the other way, it's getting higher and higher and higher and higher and higher and higher and higher. And as we keep on inching closer and closer and closer, the numbers get higher and higher and higher. The limit of the slopes is positive infinity. And as they come from this direction, slopes get higher, 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 higher. The limit of the slopes is positive infinity. So if we could find the derivative function and plug in, we would get a number over 0. And a number over 0 is what kind of limit? Infinity. Which means the derivative has a vertical asymptote at 0. That's one way. There was one more function. Did you guys find the other function? It wasn't just cubed root. Actually, there's 2 more. Tangent inverse, he would have an infinite, and square root of x. Square root of x would have an infinite at 0. Because square root goes closer and closer and closer. So far, all of those have vertical tangent lines, right? So all of those have vertical tangent lines. So when's one time that a derivative will not exist? When there's a vertical tangent line, and vertical tangent line means the derivative will be infinite. We'll have a derivative dy dx has a VA at that point. That's one case. But can I show you another function that has a non-existent derivative from your basic graphs? Oh, who's that guy? Absolute value. What's wrong with him? So far, all I've talked about is when the slope could not exist. Now I'm going to talk about when the limit definition does not exist. What has to be true for limits to exist?
Yeah, the approach.
They must agree.
It has to be an at and it has to be an approach.
Careful. Derivative talks about slopes, right? slopes from either side must agree. Why did I write positive infinity for this dude? For the derivative. Coming from one side, what were my slopes approaching? Oh, steeper, steeper, steeper is positive infinity. Because they're positive slopes, right? Uphill slopes getting steeper and steeper. How about from this side? Uphill slopes getting steeper and steeper. They agreed from either direction. What's the problem of this guy? There's a sharp point. And is there any curvature to an absolute value? So is there any converging to or coming together of these two sides? Technically, let me show you real quick. Didn't we talk about how the absolute value function of x is actually a piecewise function of a positive x and a negative x, if it's sometimes staying the same and sometimes flipping? Do you guys remember that? Absolute values, just in general. Sometimes they are staying the same, y equals positive x, and sometimes they are flipping, y equals negative x. Can I show you what the derivative would be? The derivative. I'm not going to show you what the function is. We haven't learned how to do that yet, but I can tell you the derivative, which is the slopes of the tangent lines. Guys, isn't this just a line? Up 1 over 1, y equals x. Yeah. So isn't the slope on this side just 1 for all the x's greater than 0? What are all the slopes on this side, though? Negative 1. That's just by using our understanding of slopes. For x less than 0. Why am I not putting an or equal to for the derivative? What needs to happen as I approach from either side? A limit to exist, I must have agreement from either direction. But what's going on at 0? Infinitesimally close below is going to be saying negative 1. Infinitesimally close above is going to be saying positive 1. What if you looked at a table and as you got closer to 0, negative 1, positive 1? Are they agreeing? No. At 0, they're disagreeing. Disagreement and a limit means D and E. So therefore, this one, it's not that the derivative equals infinity, and so it doesn't exist. In this one, the derivative literally does not exist. This one was a VTL, a vertical tangent line. This one was a sharp point. Whenever you have a sharp point on a graph, the derivative does not exist because from one direction it's saying one thing, from another direction it's saying another thing, and because of the limit definition of a derivative, even if the math seems to give you an answer, it's wrong. It's wrong. So let's come up here to this card that you guys were writing, yeah? Because all of this is when will the derivatives not exist, because over here I had differentiable when the derivative does exist. So this forever card says the connection between differentiability and continuity. If a function is not continuous, aka if there is a discontinuity, removable or non-removable. Ooh, last chapter stuff. If a function is not continuous, if there is a discontinuity, a jump, a break, a hole, a vertical asymptote, the derivative cannot exist, aka the function. Remember, differentiable is an adjective. The function is not differentiable at that point, aka able to be derived, aka the derivative exists. Nope. The derivative will not exist if the function is not continuous. If the function is continuous, it may be differentiable. And we're going to put watch out for ... We're going to talk about these two guys, the vertical tangent line and the sharp points. And then last but not least, if the function is differentiable, able to be derived, the derivative does exist at a point, then there must be continuity, or else it would have been canceled out. So what are my watch out fors? One of my watch out fors is going to be my VTLs, vertical tangent lines, where my derivative, aka my slope, is plus or minus infinity, is infinite. In the olden days, we would have said undefined. Whatever. And if you guys want to, you can put whatever you want from down here as far as an illustration for your studying purposes. I won't necessarily make you do this on a forever card, but it would be good to be like, oh, hey, look down below, there's an example. And maybe you did other examples like the square root function or the tangent inverse function. Functions where the slope literally does go vertical, and since it goes vertical, that derivative will be infinite. AKA not equal to a number, AKA not existing as a constant. But the other watch out is going to be our sharp points. And our sharp points, oops, that's not how you spell points. You're welcome. Here. Sharp points are going to be when the derivative does not exist. When the derivative does not exist. And if I were you, I would put in parentheses something about piecewise not, oh dear, agreed. Sorry. That's rough. I apologize. But still, once again, you're just drawing your attention down here, being like, hey, the slopes do not agree. So this one, the slope does not exist. This one, the limit does not exist. But technically for both of them, the derivative does not exist. Okay, I think that's good enough. That's forever card number, unless I add something extra to it. I mean, it still is forever card number 9, but forever cards are always a work in progress. And the reason why we have a forever card on this is because the AP loves to do one of those, like, hey, which of the following are true? 1, 1 and 2, 1 and 2 and 3. And they have these words in them: differentiable, continuous, must be, might be, sometimes, always, never true. Ugh. It's complicated, so hopefully that card will help you with that. Kiddos, let me see what else I have as far as examples. So we still have about 10 minutes, but I don't want to. I think I just have examples. Cool. You guys ready to play?
Yes.
Anybody still writing anything down from the forever card? Going once, going twice. I think a couple people are. Let's start with this example. Let's just keep it in our notes and let's do it all together. What's being asked for? Adam, this is for you. All of these are section 2.1 problems, aka using the limit definition. Do we always, forever, for the rest of time, are we going to be doing the limit definition? No, we're going to learn basic rules starting in 2.2, starting in 2.2, going to 2.3 and 2.4 and 2.5. But for right now, how are we solving the derivative?
Just fading away.
Yeah. And hold on, when this one says find f prime of x, can I go do the f prime of a definitions? We have two different forever cards, right? We have the f prime of x one, and then we have the f prime of a. Can I do straight to f prime of a if they tell me that? No. Okay, so the only thing that you can ask yourself is, do I want to do the h or the delta x? And the answer is h. I figured. So the limit as h goes to 0 of 1 over. How are we doing it plugging in, guys? Are we doing okay with x plus h needing to go inside the function wherever the argument is? Are we okay with that?
Yes.
If not, are we going to come in and let me get a whiteboard out and take you back and solidify your foundation in math and algebra? It's important and it's tricky, and I'm not saying that tongue in cheek or in any sort of derogatory way. I'm saying it as in, I know some of you will struggle with this. You need to come get help. F of x plus h. What f? What am I going to multiply by? Top and bottom? To simplify my complex fraction, because this is a 0 over 0. Keep going. Keep going, man. I gotta multiply by both denominators. I gotta get rid of them both. Just like we did in the summer review package. Some of you didn't take that seriously enough. Complex fractions. It's a thing. It's a thing that we're gonna have to use. Could you get common denominators? Put the h over 1 and multiply by the reciprocal? Yes. Have a way that works with you. And if you don't know how to do complex fractions, come in. Let's whiteboard. Do it now. Don't delay. Don't put it off till another
Don't
day.
wait, call me.
Okay. What do I have to do to this guy? Bottom's easy. What do I always do to the bottom? Yeah, I can just, well, I can do it in whatever order I want, but I just rewrite it. I'm not foiling, I'm not simplifying, I'm just leaving it as is because my goal is to get rid of that H soon, right?
Mm-hmm.
Oh, don't forget to write that. But on top, why am I putting big old parentheses?
So you know it's
This whole thing has to go to both. When I multiply the first time, the x plus h squareds cancel and x squared is left. When I multiply the second time, the x squareds, I should say, reduce, and the x plus h squared remains. Oof. What do you have to do?
foil.
You gotta FOIL to simplify and distribute the negative, right? So are you guys okay if, I know I'm doing like CalcChat math, but it's a thing in class when we're going fast. When I FOIL this guy, it's gonna be an x squared with a negative. When I FOIL this guy, it's gonna be a 2hx with a negative. Or xh, you can say. Multiplication is commutative. And then I have an h squared with a negative. I FOILed, distributed my negative, and now I'm going to cancel. That's canceling. Going to 0. What am I going to really hope there's left in common of the remaining terms? And there is. If you are very careful, you can reduce, but I don't trust most of you. Love you, but I don't trust you. So, factor out an h first. I just need a little more room. Factor out an h first, then reduce. When you factor out an h and you reduce, you should end up with a negative 2 minus h all over x squared times x plus h quantity squared. The limit as h goes to 0. At this point, it's time to plug and chug because my h's that came out and reduced are gone. Oh, I'm silly, I didn't write it. H came out, reduced, negative 2x minus h. Got it. Plug it in, negative 2x all over. Huh, isn't that going to be x to the 4th?
Yes.
It's the same thing as negative 2 over x cubed. Whew. I wonder if those of you guys who are budding power rulers and basic rulers could have taken this function, rewritten him just a little bit, and maybe gotten here. You guys should go straight a little bit quicker. Couldn't this have been x to the negative 2? Power rule. Don't worry, we're seeing it soon. Next section. A lot nicer than all that work. Anyway, coming back. How do I find a tangent line? Well, first let's find me a slope. Although, don't we need a slope and an x1 and a y1? So when it says at x equals a, we know that x equals 1. How am I going to find my y? Plug it in, f of 1. So isn't that going to be the same thing as 1 and, what's 1 over 1 squared?
1.
Ooh. So I have my x1, I have my y1 by plugging into my function. I'm going to find my m by plugging into my derivative, and my derivative is this dude. So therefore, negative 2 all over 1 cubed equals negative 2. You guys agree?
Yes.
At this point, it's easy. It's like, okay, y minus the y1 equals m times x minus the x1. And we already talked about how we don't need to. Let's just stop. This here is going to be affectionately referred to as sticking it to the man. Nice thing is, on the AP exam, when you get to the long answers, you don't have to simplify. You can give it to them and be like, you just asked for the answer. You didn't say how nice you wanted it. There, you figured out if it's right. No. They actually, anybody who's ever gone to the AP grading in Florida has come back to their students saying, don't you ever addition, subtraction, multiplication, division, no. Because they graded so many exams where a kid made an addition mistake and had done the calculus right and lost it. They have to. And they've had places where the answer was right ultimately, but they had done some error in logic, like rewriting the limit. It was right, but by not rewriting the limit, technically the limit is not equal to the function. That is a fallacy. That is a breakdown in the proof, in the logic to the answer. And so if it was a problem where the answer wasn't the only points, but the work was part of it, they've had to mark off kids where it's like, why didn't you rewrite the limit? Why didn't you do this? Why didn't you do that? Because the people grading. Not only does the answer have to be there, not only can the answer not just appear, but also have to be your final result, but every single piece in between has to be right. Anyway, long story short, stop. Okay, what's going on down here where it says find where the function is parallel? Come on, your brain's parallel means same slope. Oh! Same slope. Well, I don't know his slope until I get y equals mx plus b, right? His slope is -2. Of this line is -2. What needs to have a -2 slope? Look at the noun.
Function.
The function. Wow, grammar's helpful. Who's the function? This guy. Where's his slopes? Right here. Doesn't this express the slopes of the function because it's known as the derivative? Right?
Yeah.
How do I figure out where the function is parallel? Look at his slopes, the derivative, and set equal to what I need the slopes to be. Oh, no big deal. -2 over x cubed needs to be -2. So I can multiply by x cubed, I can divide. It's the same thing as when x cubed is going to equal 1, and that's going to occur at x equals 1. Dun, dun, dun.
Dun, dun.
Oh, that makes sense because -2 was the slope we were just talking about. Guys, that's one type of example. There's only one more that I was hoping to get to today. But how different is the directions?
Not very.
Not very, except in this one. Did it ever say that we had to find f prime of x?
No.
No, so couldn't you technically just go for f prime of a at the beginning? If you wanted to be snazzy, you could have even done the limit as x approaches a of f of x minus f of a. And maybe your math would be even a little bit easier. How do you graph a line? You put it in your calculator. How do you graph a function? You put it in your calculator. How do you sketch it? You sketch it. All right, fine. Homework, due tomorrow. But there's a 0 period, so not a bad idea to try it, attempt it, bring it in, and say, help BCers or other ABers. If you get stuck, I'll see you guys later. Remember, in the morning, Google Classroom doesn't need to be submitted until 8. And it's just the attempt to do the best you can.
Yes, Miss C.
But look at my comments. If you're not writing directions, problems, details, attempt.
Who do you think approximate?
Losing points. Don't lose points. Bye guys, happy Tuesday.